A midnight refresh flips a single digit on a live tracking dashboard, and the chat thread goes silent. The predicted point for 3I Atlas, our interstellar visitor, slips a few tenths of an arc-second off the new measurement. One residual is noise. 3 in a row make a trend. By the fourth, someone unmutes and says what everyone's thinking. The comet's non-gravitational push just eased off. The interstellar sprinter is coasting. The slowdown is real. Here's the twist. This isn't a software hiccup or a bad flat. The new astrometry folds in cleanly from multiple sites, and when you refit the orbit without prejudice, the sunward acceleration term collapses by roughly a third compared to last week's best model. The staircase of thrust pulses we mapped near perihelion, short CO2-led kicks spaced by hours, has thinned. The steps are shorter and the rises are lower. The nucleus is still venting. The chemistry hasn't gone mute. But the meter that measures how hard those vents shove the comet has dropped. Roll back 10 days to make the contrast sharp. During perihelion week, the geometry did us favors. Mars sat in a forward-scattering sweet spot, while Earth blinked into conjunction. CO2 lines surged in hours-long bursts with barely a dust echo, and orbit fits improved when we allowed discrete sunward thrust pulses. Photometry showed the corridors flattering on dust. Spectroscopy nailed the gas. Astrometry saw the clicks in speed, each on the order of a tenth of a millimeter per second. Stack half a dozen, and you could feel the path bend. It was the neatest link between chemistry and dynamics we've had for a visiting comet. Now the plot line jogs. The freshest frames show 3 things at once. First, the total CO2 production is still healthy, but the peak-to-valley contrast across a rotation has flattened. Second, water has crept up a notch, not enough to take the wheel, but enough to matter. Third, the cadence of the thrust pulses has drifted, and on a few spins, gone missing. Put those together, and slowdown becomes less mysterious. You don't need drag to slow a rocket. You just need the thrust to pivot or stutter. Make the 3D situation feel real. Picture the solar system as a tilted vinyl record. We're near the rim. Atlas is skating across near the grooves, but retrograde, passing inside Mars's orbit at closest solar approach. 2 weeks ago, the Sun corridor lined up so Sun, comet and observer stacked in a narrow slot. Sunward jets projected cleanly onto the line of sight, and forward scattering made small dust look brighter than it deserved. Today, the corridor has slid on. Phase angles are softening. Elongation is widening. The same vents now push at slightly different angles and with less help from projection. Even if the gas output stayed constant, the way we measure its shove changes as the geometry unwinds. But geometry alone won't buy this slowdown. The fitter's already correct for projection. What's left are physical changes on the surface. 4 concrete mechanisms can tame the thrust without killing the gas, and the data point at all 4 in different proportions. First, the valves are crusting. Early in, CO2 vents looked like thresholded cracks. Quiet on, then off. Those digital pulses demand a brittle lid that pops once per rotation when a beam of sunlight hits just right. Over time, grains settle and frost redeposits around the throat, narrowing the opening. The same heat no longer tips the system so decisively. Vents still breathe, but the on-off curve blurs. The gas rises and falls, not snaps. That takes the edge off the thrust steps. Second, torque is moving the target. Every jet is both a push and a twist. Stack a week of pulses and the rotation period changes by fractions of a percent. That's minutes on a 9-hour day. Shift the day, and you shift when a given crack meets the sun square on. If the peak used to land at local noon for that fissure, it now lands at late morning. Less time at perfect aim equals less momentum transfer, even if the total gas over a day is similar. In the residuals, that looks like pulses that arrive late, then shallow, then disappear for a turn. Third, plumbing has connected. Those shallow CO2 pockets we suspected, pressurized, sitting just below the skin, empty fast once a seam opens. Heat propagates, pressure equalizes, and neighboring pores begin to talk to each other. What was a narrow jet becomes a wider seep. Chemistry holds, but thrust efficiency drops, because broad vents leak in many directions at once. You still see CO2 in the lines, but the vector sum of all those tiny pushes cancels more than it used to. Fourth, water is joining, not as the boss, but as ballast. If deeper H2O ice has started to sublimate in earnest, two things happen that matter to dynamics. The first is simple. Water's lower thermal speed and different vent geometry can produce jets that point elsewhere than the CO2 ones, blurring the net push. The second is subtle. Water can drag more dust. Dust mass lifts slowly, but once it does, fallback coats vent rims and resculpts cracks. A millimeter of new lag along a throat is enough to tilt the local nozzle or damp the on-off behavior we loved near perihelion. Numbers make this less hand-wavy. Near peak, a strong pulse might have delivered a thrust of a few tens of newtons for 2 hours, enough to give a city block nucleus a tenth of a millimeter per second of delta V. Halve the vent efficiency by widening the aperture and adding dust, and you're at a few newtons. Stretch the active window from 2 hours to 4 by blurring the threshold, and you deliver the same total gas with less peak kick. The orbit only feels the peak. Smooth the pulse and the Fitz sunward term falls, exactly what the dashboards are telling us. Let's talk verification, because a slowdown is the kind of claim careful people try to kill before they say it out loud. The first check is internal consistency. Do independent sites with different plate scales and star catalogues land on the same sign in the residuals? They do. The second is model robustness. If you let a blind, piecewise thrust model choose when to push, does it still pick fewer or weaker pulses? It does. The third is chemistry. On nights where spectra show a low-contrast CO2 light curve, no sharp spikes, the orbit fits show shallow or missing steps. The fourth is geometry. Correct for phase and elongation, and the slowdown remains. When 4 knives cut the same way, you sharpen them. You don't blame the cutting board. The most tempting wrong answer is drag. Space isn't empty, but it's empty enough. There is no ambient gas thick enough at 1.5 AU to break a boulder. What can drag is your own coma. Recoil from gas molecules colliding with grains, re-impact of dust onto the nucleus, even outflow shadowed by topography. But those are just other words for the vents changed. The only real break here is the loss of a clean nozzle. You're right to ask about the nickel lines we've been watching since the Mars pass. They're the quietest barometer we have for the crust. In the new stacks, nickel holds roughly steady while CO2 smooths. That argues the chemistry at the very surface hasn't flipped. The carriers, whatever makes Nye easy to free, are still feeding the gas phase. The geometry of the vent is what's evolving. If iron wakes, even weakly, as water climbs, the Nye-Fe ratio will drift towards sanity and confirm that deeper, hotter layers are finally participating. If iron stays scarce while water inches up, the crust's fractionation story gets another chapter. What about the green radicals, the CN and C2 bands that give comets their emerald glamour in big images? So far, they're still shy. That's useful. If dust were truly surging, or if UV photolysis of parent molecules had jumped, you'd expect those bands to mirror the dust's mood. Their continued quiet alongside a dynamic slowdown is a clean separation. Geometry and plumbing are moving the vectors. Chemistry is playing a slower game. There's a more subtle slowdown buried in the light curves that matters for modelers. Spin evolution. If the day length is drifting, you can watch the rotational phase of whatever periodic signal you trust. CO2 modulation, a faint photometric wave from an elongated shape, and measure a spin down or spin up. In the latest runs, the best fit period has lengthened by a hair, on the order of a few minutes over a week. That's enough to smear any crack-gated noon and steal the crispness from a pulse. It also tells you where the bulk of the torque lives on the surface, likely at mid-latitudes where projection onto the spin axis is efficient. Why should you care beyond the neatness of the fit? Because this is how we turn a fast visitor into a physical object with a map. A slowdown forces models to include vents that evolve. Valves must become pipes. Cracks that opened at one longitude now connect to neighboring pores. The torque tells you where those systems live. The chemistry tells you what they're made of. The dynamics tell you how wide they've gotten. When you see the sunward term fall at the same time the hot band ladder in CO2 shrinks and the 3.1 micron ice grain dip persists, you've learned that the comet is not shutting down. It's widening and cooling its nozzles while still carrying frost. This is also where the engineered frame often knocks on the door. A sudden loss of thrust reads like a throttle down. But look for the habits of control. Sustained accelerations decoupled from gas lines, coherent changes in direction rather than magnitude, signatures outside the spectrum, narrowband radio, specular light curves that say hardware. We don't have them. We have gas that still flares, dust that still reddens, and a push that's less efficient because the cracks that gave us clean nozzles are healing, slumping, or multiplying. Sloppy plumbing, not steering. If you want to track this from a backyard or a small observatory, now that elongation is creeping past 30 degrees, a practical plan helps. Go pre-dawn, east-southeast, low but improving each morning. Expect around magnitude 12. Give or take a fussy sky. Stack many short exposures. Gradients at that altitude are merciless. Anchor your photometry to nearby standards and repeat it on 3 mornings in a row. If the light curve's slow trend fades faster than the gas reports coming from proteins, you'll have caught geometry letting go, the corridor's forward-scattering boost slipping away. If the coma's total flux holds while the orbit fit's thrust term falls, you've witnessed the core of tonight's story. Plumbing, not production, drives the slowdown. If you run a spectrograph, 2 windows pay rent. Blue-violet to set limits on CN and to peak for any lingering nickel lines. Near IR for continuum color. From the ground, you won't catch the 3 micron ice band cleanly, but you'll see whether the slope neutralizes as grain sizes shift. For the timing obsessed, try for a rotational light curve with cadence fine enough to pick up a few % modulation over several hours. A period change is the kind of receipt that turns a qualitative "the pulses feel weaker" into a quantitative "the valve moved." There are failure modes worth naming so you don't fool yourself. Early morning sky flats must match the target's altitude, or your gradient subtraction will fake a slowdown by over-flattening the coma. plate scale shifts masquerade as residuals. Resolve your plate every stack and log star catalog versions. Rotational aliasing is sneaky. If you always shoot the same hour, you'll sample the same surface longitude and either always catch or always miss the pulse. Stagger by a couple of hours across nights and resist fitting away what you don't understand. A too eager background model will eat the very low contrast changes we're chasing. What could genuinely shock us from here? A reversal. If the thrust term drops to near zero and then snaps back at a new phase a day later, you're watching an active region go dark while another lights. Geomorphology in real time. If iron suddenly appears even as nickel fades, deeper, hotter layers have cracked, and the metal story will tilt toward normal. If water surges and the CO2 with H2O ratio plunges, while the thrust term keeps dropping, that says the nucleus is heating into a broad, inefficient venting regime where gas comes out everywhere and the vectors cancel. Least likely, but loudest, would be a measurable acceleration that points away from the sun without a matching gas signature. That would force a top-to-bottom rethink. The data on the table don't lean that way. Loop back to the opening moment, a live tracking dot stepping off its predicted path the wrong way. Slowing down is not a failure, it's a diagnosis. Near perihelion, Atlas gave us discrete valves, CO2 jets punching like metronomes and nudging the orbit in clicks. Now, as the corridor slides and the vents wear in, the system looks more like porous rock on a warm afternoon. Many whispers instead of a few shouts. The push softens. The path hews closer to gravity. The surprise is not that physics caught up, it's that we were lucky enough to watch both regimes in one passage. When you stand under a crisp, pre-dawn sky next week, with a mug cooling too fast and a mount humming, remember what slowdown means at a few 100 million kilometers. It means frost redeposited along a crack that used to whistle. It means the comet's day got a few minutes longer and put noon out of reach for a favorite vent. It means pockets that yelled now murmur into a wider room. It means a traveler from another star, still breathing, is teaching us how cold plumbing evolves when sunlight finally finds it. If wonder with receipts is your thing, this is the cleanest kind. Watch the non-grav term in the orbit solutions. Watch the CO2 curves contrast. Watch for water's quiet climb and iron's first whisper. If you're taking data, be the cadence. If you're modeling, be the error bars. The slowdown is not the end of the story, it's the hinge. On the far side, we'll either see a gentle fade into ordinary behavior or a second act where new vents take the stage. Either way, we'll keep the units tidy, the claims modest, and the light curves honest. That's how you learn from a slowdown. Jezai, 3i Sui, Atlas. The worst theory grows with each new image beyond the Atlas. Zai. It starts with a coffee-stained laptop and a message that pings 3 time zones. Zoom in on the core. The image is pretty in that dangerous way. Faint comets are pretty. Soft coma, a hint of tail, stars stretched into short dashes by tracking errors you only notice if you care. Someone drags a slider too far. Contrast pops. The nucleus hardens into a squarish glow with twin ridges on either side, like struts on a satellite bus. In the chat window, a sentence appears that you've seen too many times this month. This doesn't look natural. And with each fresh stack that hits social, the worst theory grows another layer of certainty. Here's the twist. The thing that's getting louder is not the comet. It's the geometry and the processing. 3i Atlas is still the same object, retrograde by a few degrees, hyperbolic, inbound at tens of kilometers per second, perihelion near 1.4 AU, and now easing out of the blackout that je zei. Kun je een script van maken met 55,000 woorden? Beyond the atlas, zei, it starts with a coffee-stained laptop and a midnight Discord ping. Zoom in on the core. The new stack from a backyard rig in Nevada pops open. 40 minutes of data on 3i atlas, guided, dithered, and sharpened. Someone pulls the contrast too far. The coma collapses into a boxy glow with twin ridges, like struts on a satellite bus. The chat scrolls. That doesn't look natural. 10 minutes later, a second image drops from a scope in Spain, then a third from Chile. Each one, stretched to death, shows the same square-ish heart. The worst theory, that an engineered object is hiding in plain sight, gains a follower with every screenshot. Here's the twist. The comet didn't change shape overnight. Our tools did. The geometry moved fast, the air was unkind, and the processing chains were dialed past the point where pixels tell the truth. It's a perfect storm for pareidolia, a faint, compact source low in the sky, imaged near the sun's glare, pushed through aggressive deconvolution and AI denoising. The struts are math. The bus is a point spread function with its mask showing. The more we stare, the worse the theory grows, not because the comet is weird, but because human vision is. Let's rewind to what we can pin down. 3i Atlas is on a hyperbolic orbit, retrograde by a few degrees relative to the ecliptic, moving at tens of kilometers per second with respect to the Sun. Perihelion lands near 1.4 AU. Around late October, Earth slid into a blackout window. Solar elongation dropped under 30 degrees, then hit conjunction. Most of us lost contrast right when chemistry and dynamics were changing fastest. Mars had the better angle for a few days. Earth did not. Now that the elongation is widening again, pre-dawn sessions are back on the menu. Low, hazy, and hard. That's exactly when rectangular ghosts appear if you go hunting for them. Discovery and verification usually live in the boring parts of the workflow. Who saw what first? A handful of smart scopes in the American West posted early recoveries as the window reopened, reporting magnitude around the low teens. A few mid-size observatories added deeper stacks, noting a compact coma and little tail structure. 2 nights. Later, the first square core crops appeared. Rare at first, then common as others tuned their sliders to match. Confirmation didn't come from a new physical feature. It came from the same processing habits traveling through different hands. Let's make the 3D situation intuitive. Picture the solar system as a tilted vinyl record. We're near the rim. 3i Atlas is skimming the grooves retrograde, wrong-way traffic, slipping inside Mars's orbit at solar closest approach. For a couple of weeks, Earth's line of sight ran near the Sun. Even now, just after conjunction, we're shooting through thicker air and punishing phase angles near dawn. That geometry loads your frames with gradients, forward-scattered skylight, and a swollen point spread function. You can fight those with flats, background models, and careful masks. Or you can crank deconvolution to 11 and watch the PSF ring like a bell. 4 crisp beats explain why images went square. First, PSF shape and deconvolution. Telescopes don't draw points. They draw little diffraction maps. On refractors with field flatteners and compressing optics, the PSF can pick up subtle rectangular symmetry from lens groups and sensor microlenses. On reflectors with spider veins, the PSF carries faint spikes. Deconvolution algorithms like Lucy Richardson and Wiener sharpening assume a PSF and try to unsmear the image. If your PSF is wrong, or if the signal is low and the noise is high, the algorithm invents structure. Edge ringing turns round things into diamonds. Undersampled stars sprout box corners. A faint coma with a bright center becomes a square with ribs. Second, pixel grids and resampling. Most rigs shoot on Bayer-pattern CMOS sensors with micro-lens arrays. When you debayer, drizzle, and upsample, you push the image onto a new grid. If you then noise reduce with a block-based filter or an AI denoiser trained on sharp edges, the grid leaks back in. Compression adds its own scars. H264 macro blocks and sharpening kernels can imprint 8x8 or 16x16 geometry. Stretch a low SNR core hard enough and you'll see the lattice. Third, tracking, guiding, and drizzle. Guiding corrections are quantized in tiny steps. Near the horizon, refraction shifts positions between sub-exposures. When you drizzle to recover resolution, you're combining shifted, undersampled frames. If your dither pattern repeats and your rejection thresholds are tight, you can carve the central PSF into a square as overlapping outliers clip the corners. It looks like structure. It's your registration mathematics showing through. Fourth, gradients and AI. Near dawn, sky brightness changes across the field. Gradient removal works, but only if you're gentle. Many imagers now run smart denoisers and detail enhancers trained on terrestrial photos. Those models are masters at turning fuzzy blobs into crisp patterns. Give them a small, round glow on a tilted gradient, and they'll hallucinate. Edges, ribs, and panels. You asked for signal from noise. They obliged. Before diving into the engineered frame, take a breath and measure. If a rigid shape is real on the sky, 3 predictions hold. 1. Orientation. The structure keeps the same angle on the detector as the field rotates, or on equatorial mounts, maintains a fixed position angle relative to celestial north across the session. 2. Wavelength. The feature persists across filters and bands, not just in one color where PSF weirdness is strongest. 3. Sampling. The feature strengthens with better sampling and higher SNR, not only when you push the stretch until stars go square. The current crop fails all 3 tests. Flip the camera 90 degrees. The bus rotates with the sensor. Swap from luminance to R or I band. The struts fade. Integrate 2 hours at high altitude with gentle processing. The square melts back into a round core and a soft coma. Now the geometry again, because it's the quiet villain. Forward scattering, the way dust gets brighter when the sun is behind it, was peaking for certain lines of sight as Earth crawled out of conjunction. That boost makes small grains sparkle and swells the inner coma relative to the outer glow. It's easy to mistake that concentrated brightness for a compact, resolvable object. Add low elevation and a fat air column, and your PSF fattens asymmetrically. If you try to fix that asymmetry with a symmetric kernel, ringing picks a shape and repeats it. What about those twin ridges people point to? Struts running off the core. 3 natural culprits show up in stacks, guiding spikes from intermittent corrections, which create small repeated elongations along RA or deck. They look like rails if you stretch hard. Residual star streak subtraction. Many folks shoot on comets at non-sidereal rates, then subtract stars. If your star mask is too aggressive or your kernel is too big, you carve rails on either side of the moving source. Spider diffraction. Newt users, your veins are real. At low SNR, the inner coma can inherit the spike geometry. Deconvolution exaggerates it. There's a 5th, internal reflections. Bright stars just off frame throw ghosts across the field, especially with reducers and correctors. Those ghosts often come in pairs and pick up the rectangular shape of the sensor window. Put a ghost near a faint coma, stretch, and you'll swear you see scaffolding. So, what's the fair take on the worst theory? That the core is engineered. You don't rule out exotic ideas by snark. You rule them out by receipts. If a rigid object were sitting at the heart of the coma, we would expect coherently directed, sustained accelerations decoupled from gas production, radar glints or occultations inconsistent with a fuzzy nucleus, narrow-band radio emissions that don't belong to the Sun, Jupiter or any spacecraft, and reflectance spectra with sharp, flat features, unlike powders and ices. We don't have those. We have CO2-led gas, water waking slowly, nickel lines without iron twins at first, and non-gravitational nudges that line up with when gas vents do. The images aren't telling a different story. Our processing is. What actually changed on the comet over the last couple of weeks is more interesting than a Photoshop square. During perihelion week, CO2 outbursts came in steps, valves opening for hours, then closing. Those pulses nudged the orbit by fractions of a millimeter per second each. As the days went by, water joined gently, the step edges rounded, and the sunward acceleration term fell by a third. That slowdown didn't need drag, it needed plumbing evolving from narrow jets to broader seeps. That's the physics we want to learn. That's where images can help, if we stop teaching them to lie. Here's how to shoot this target without growing the worst theory. Keep it low gain. Set conservative stretches. If you can't see it without a brutal contrast push, it's probably not real. The coma is a gradient. Respect it. Measure your PSF. Shoot a bright star at the same altitude and azimuth, same focus, same filter. Use that PSF for any deconvolution. If your deconvolution makes the star square, stop, rotate and repeat. If a feature rotates with the camera or flips with a meridian flip, it's you, not the comet. Intentionally rotate by 90 degrees halfway through a session to test for sensor-locked artifacts. Cross-filter, grab L, R and I, or Sloan R and I, back to back. PSF asymmetries often shrink in redder bands. A real structure holds across color. Avoid over-drizzle. Drizzle helps undersampling, but it also amplifies grid ghosts. Try native scale with gentle sharpening before you 2x everything. Be kind to denoisers. AI detail enhancers can hallucinate panels. If a slider makes the coma click into a shape, you've told a network to draw for you. Log your air mass. Anything under 25 degrees altitude is a PSF war zone. If your best structure lives below that, don't put it on the internet without a caution label. Use comet-aligned stacks and star-aligned stacks. Compare both. Features that shift or smear differently in the two stacks are more likely to be processing artifacts. For spectroscopists and photometrists, this is a gift, not a headache. A compact coma near dawn means you can extract clean inner coma spectra if you keep the slit steady and log your sky gradients carefully. In the blue-violet, check CN at 388 nanometers. In the green, look for C2. In the near IR, track the continuum slope. You won't see the 3.1 ice band from sea level, but you can see where the grains trend toward larger sizes as water wakes. For photometry, anchor your measurements to standard stars at similar color and air mass, and repeat on 3 mornings. A true change in the inner coma profile will march night to night. A processing ghost will not. Let's weigh competing explanations honestly. Natural mechanisms. PSF asymmetry, deconvolution ringing, sensor grid artifacts, spider diffraction, guiding rails, internal reflections, forward scattering, low altitude seeing, and compression. Each is enough to square a star. Together, they can square a comet. They vary with altitude, filter, orientation, and stretch. Engineered frame requires independent orthogonal evidence, dynamics decoupled from gas, signals outside optics, resolved structure that respects sky geometry across instruments and bands. Absent. Hybrid stories, a natural comet hiding a rigid core, have to pass both sets of tests. They don't. If a solid bus lived inside, you'd see its light curve beat against the coma as it rotated, unchanged by filters, unchanged by camera rotation. You'd see its orientation persist across long integrations. You'd see its signature in polarimetry. We don't. Constraints matter. The object is faint, low, and near the sun before dawn. That means gradients, air mass, and short sub-exposures. You fight that with patience, not with sliders. If you're tempted to run a local contrast enhancer because the image looks soft, a better move is to gather another hour of photons. What should you actually watch next if you care about reality and not retweets? The ratio of CO2 to H2O as the comet warms post-perihelion. If water climbs and CO2 holds, we're watching insulation give way to deeper ice. If CO2 stays king, birth chemistry or a stubborn crust is in charge. Nickel versus iron. If Phi I finally appears while Ni I holds, the metals are moving toward normal as deeper, hotter layers vent. If Ni stays alone, the crust remains fractionated, the cadence of non-gravitational pulses. If the staircase spacing drifts, torque is changing the day length. If the steps vanish overnight, a vent widened. Plumbing switch, not propulsion. The green radicals. Cn and C2 lighting up would mark a change in parent molecules or UV pumping, not in PSF magic. If they remain shy while dust brightens, you're watching geometry, not chemistry. The dust slope. A neutralizing continuum as the comet climbs to higher altitude on your horizon suggests larger grains or less forward scattering boost. A persistent red slope says, fine dust remains dominant. If you want a concrete backyard scale experiment that answers the square core meme with receipts, do this. Night 1. Shoot 45 minutes in L at 20 degrees altitude. Then rotate your camera 90 degrees and shoot another 45. Stack each set separately, comet aligned, same processing. If the struts rotate with the sensor, they're yours. Night 2. Shoot Re and I back-to-back at 25-30 degrees altitude. Build stacks with identical drizzle and deconvolution settings. If the shape softens in EU while holding in arc, you're looking at PSF color dependence, not metal beams. Night 3. Climb to a darker site or wait for a morning with very dry air. Repeat Night 1's settings, but keep processing. Gentle. If the square disappears with better seeing and altitude, you've solved it. Share the full stacks and your logs. Air mass, PSF star, decon kernel, drizzle factor, denoiser settings, alongside the pretty picture. That's how you keep wonder honest. What would genuinely surprise me? A resolved, sensor-invariant structure that holds across filters, across altitudes, and across instruments. A persistent, non-sunward acceleration with no gas signature. A polarimetric pattern in the inner coma that screams flat facets, not fluffy grains. Or a radar echo inconsistent with an unconsolidated surface. Those would move the needle. Stretch-induced squares do not. So let's close the loop on the claim that the worst theory grows with each new image. It grows with each new overcooked image. The geometry drove us low on the horizon and close to the sun. The physics gave us a compact, bright inner coma. Our algorithms did the rest. We sharpened, we denoised, we deconvolved with the wrong kernel. We resampled. We saw a box because we asked the machine to draw us one. If you're Alex, standing in your driveway before dawn with breath fogging the eyepiece and a tracker humming, you don't need to carry that weight. Take the long route. Shoot short subs. Dither. Plate solve. Keep your flat fields honest. Build the stack you can trust and let it look a little boring. Reality often does. Then watch the numbers, not the vibes. The CO2 curve, the faint blue radicals, the slow creep of water, the tiny changes in the orbit fits. Those are the receipts. Those are the lines that teach us how an interstellar snow and rock time capsule wakes up when sunlight finally finds its cracks. And remember the geometry tax. For weeks, we peered down a corridor that boosted dust and punished contrast. As that corridor slides away, your stacks will look cleaner at the same settings without any miracle in the sky. The right response isn't to crank the sliders harder to keep the drama. It's to turn them down and let the comet be what it is. A faint, fast traveler, round at the core because physics prefers round, messy at the edges because vacuum prefers leaks, surprising in chemistry because it froze under rules that weren't ours. If wonder with receipts is your thing, this is the moment to choose the receipts. Be the cadence, be the error bars. Post your logs with your pictures. When someone drops a square, ask for the PSF star and the decon kernel before you ask for their hot take. And when the next interstellar visitor swings through and the worst theory wakes up again, you'll know exactly where to look first. Not at the pixels, but at the angles, the air, and the math.